So we got the same type of thing we had here for igneous rocks, we have for sedimentary rocks. There's a lot going on this reference table. So I like to break it apart bit by bit, take the notes right next to the words so that it makes sense. So once again, we have another dichotomous key. Same concepts where you're going to narrow it down to one rock based on the characteristics of that rock. But this one's set up a third way. Slightly different things going on here than with the igneous rocks and the minerals that we've done so far. So let's take a step back quickly to review minerals. What was the first characteristic we wanted to look at for minerals to separate them into groups? Luster, metallic or non-metallic. What was the first thing we looked at for igneous rocks? Intrusive or extrusive. Take a look at this reference table. And this time it's texture. So once again, this is earth science. It can't be simple. Texture is not how it feels. So we're not just saying, oh, that's smooth, that's rough, that's bumpy, that's silky. None of that stuff. We are going with how they look. And our three choices here are clastic, crystalline, and bioclastic. Any idea what any of those words mean? No. What made you get that idea? Oh, last period. Got it. All right. So if you already did your started the sedimentary rock lab, okay. Let's focus on that word since that's the one Wyatt brought up. He said something about fossils. What in the name bioclastic would give anyone the idea that there might be fossils? Bio, what does bio mean? Living. Yep, like biology. That's a study of living things. So bioclastic has something to do with living. How about crystalline? Got any ideas what crystalline might mean? There's crystals. So I guess we're stuck on the word plastic. Probably means nothing to you unless you already had the lab. So we're going to start right there, maybe. There you go. So crystalline are rocks, plastic are rocks made of broken pieces of other rocks cemented together. Madison, are you cold sitting next to the open window? Okay. So that's a new vocab word that you're going to just have to get comfortable using that word. All it means is broken pieces of rocks that get glued together. Remember, guys, you're not supposed to have AirPods in during class instruction. So those of you with AirPods in, please remove them. I see several. So that is just, again, broken. That's basically the classic sedimentary rocks. Because if you remember, wanted to have this up too. Do you remember from our rock cycle chart, how are sedimentary rocks formed? How do we do this? Sedimentary rocks, how do we figure out? Go backwards. They're formed when sediment gets deposited, buried, compacted, and cemented together. So these clastic ones are just these sediments that get glued together. They're just classic broken pieces of rocks. Where crystalline are formed by chemical action. They actually have crystals in them. Now, I know you guys don't know much about chemistry yet, but if you take two chemicals together, they will form a chemical reaction, and sometimes two liquids form a solid. There's more to it than that, but you don't need to know that for earth science. So just know that they're crystals formed by chemical reaction. And then bioclastic, the last one there, formed from the remains of once living things. So again, we got that bio part, but then the clastic part. So again, we got living and pieces. So that I think is really the only new thing that's on this reference table at all. Everything else that's on this reference table, you probably could figure out without an explanation. So grain size, what do you think that is? Not how big the rock is, but how big the pieces are. So how big the pieces or the crystals are. Grain size is most important. Actually, I'm going to ask you this. Which groups, plastic, crystalline, or bioplastic, does it look like grain size is more important? So let's take a look. In the crystalline and bioplastic sections, what do you notice about all of those? All the crystalline are the same. They're fine to coarse. All the bioplastic are the same, microscopic to very coarse. So is crystal size really important for those? No, they're all the same. But up here, the plastic one, the grain size is actually what makes the rock have its own characteristics. So yes, conglomerate and breccia, they both have a grain size of pebbles, cobbles, and boulders embedded in sand, silt, or clay. They're made out of a mixture of everything. Sandstone is made out of just sand, nothing else. So sand has a crystal size of 0.0006 to 0.2 centimeters. Siltstone is made out of silt, 0.00004 to 0.006 centimeters. And shale is only made out of clay, which has a grain size of 0.00004 or less. So they're literally grouped. This section, the plastic ones, are grouped based on their grain size. So it's super important there. Whereas for the other two, grain size doesn't matter. Then we go to composition. What do you know notice about the composition of plastic rocks? All the plastic rocks are exactly the same. So all the plastic rocks, whether it's conglomerate, breccia, sandstone, siltstone, or shale, are all made of the exact same thing. Mostly quartz, feldspars, clay minerals may contain fragments of other rocks and minerals. But composition matters for the bottom half because each one has its own composition. Rock salt, yeah, the rock salt they put on the roads is made out of halite. Yes, that mineral we learned. Rock gypsum is made out of gypsum. Dolostone, dolomite, limestone, calcite, and bituminous coal made out of carbon. So composition matters for the bottom half, but not the top half. So composition, again, what the mineral is made out of. Clearly, I think you got rock name. It's the name of the sedimentary rock. You may notice I did not put a bubble for the map symbol. And for now, until about January, we're never going to worry about the map symbol for now. It doesn't show up in this chapter at all. The one thing I do want to say about it is this map symbol has nothing to do with the way the rock looks for the most part. For example, this one that has bricks, limestone, there is no rock out there that looks like a bunch of bricks. So same with the dashes. There's no rock with a bunch of dashes or a dashes and a dot. It's not. It's just literally showing that's basically a key to some maps we're going to do in chapter 6. But for now, that means nothing. So just keep in mind that it's there, but ignore it. The last section is the comment section. Comment section is, sometimes it helps, like for here, conglomerate and breccia, they have the same grain size, the same composition. The only thing that separates them is conglomerate's made out of round fragments, where breccia is made out of angular fragments. So sometimes it helps. The next three kind of really doesn't help much at all. Here it tells you how they form. The comment section might or might not help. It tells you a little bit of the rock, may help you identify it. Sometimes it won't. So just like all the other rock charts and the mineral charts that we've used so far, I like the Post-it note technique, where you look at the rock, you decide first, is it plastic, crystalline, or bioplastic? Then you look at the grain size or the composition, and you eliminate all the wrong answers, basically. So it's just like all the other rock charts we've used so far this year. All right, just to solidify that you know what these words mean, we're gonna go to the top of page 25. And at the very top where it says sedimentary rocks, I want you to squeeze this in. They're formed by the deposition, burial, compaction, and sedimentation of sediment. That's straight off the rock cycle chart. 25. Right at the very top where it's the sedimentary rock. So now, based on the notes we literally just took, we're going to just give a little bit of, it's really just review. It's almost the exact same stuff we just took notes on. How are clastic rocks separated? So if we had just those clastic rocks, how do we organize just the plastic rocks? Take a look at that reference table. You can either look at the one on the previous page or on page 7 of your reference table, which I'm putting up here now. So just these clastic rocks, the ones at the top, they get grouped by their grain size. So if you had a whole pile of plastic rocks in front of you, you would put them into groups based on their grain size. These rocks are formed by the deposition, burial, compaction of sediments. And the examples of these right off the reference table are siltstone, sandstone, conglomerate, breccia, and shale. So take a look at those crystalline rocks. So the group, just those 3 rocks just in the crystalline section. If I gave you 3 or 4 or 10 rocks that are all crystalline, how would you put them into groups? Was it based on their grain size? Did we put them into these 3 in groups based on their grain size? Nope, grain size doesn't matter for these ones. So what does matter? Composition. So those ones again are by their composition. And from the comments section, these ones are formed still from the compaction and sedimentation, but this time it's of crystals from chemical reactions. So 2 results of chemical reactions are what's called precipitates and evaporates. You might, again, this is right off the reference table. You don't actually need to know what a precipitate or evaporate is. Just know they're the result of a chemical reaction. A precipitate would be when you take 2 liquids and a reaction happens and a solid forms and it falls to the bottom of the ocean or the lake. An evaporate would happen for like rock salt. If you take salt water, what happens if you evaporate the water out of there? Your salt's left behind, so that's an evaporite. And the 3 examples are rock salt, rock gypsum, and dolomite. And bioclastic, again, if we look at that reference table, how are the bioclastic groups classified? Is it by, again, their grain size? Nope, composition again for that one. And these ones, there are two different types. They can be formed from cemented shell fragments, or the limestone, or I'm sorry, coal is formed by the compaction of plant remains. All right, everybody good? Mm-hmm. We're gonna skip the bottom for now. I wanna, oh, I guess I don't have. We're gonna go right ahead. We're gonna start your homework because this is what you're going to need to know or be able to read your reference table for the lab that you're gonna be starting either today or tomorrow. So if, I don't think I actually said this out loud yet, but I kind of think you might know it already. The sedimentary rock chart is on page 7 of your reference table. So you might want to have that out, or you can flip back to the one that we just were taking the notes on. But let's just make sure you know how to go about reading this rock chart. So we're going to start with, I already did one of them for you. I already did conglomerate. I said the grain size, I went with mixed because the conglomerate and the breccia, they're the only two that are mixed. Everybody else has their own grain size. So conglomerate is made out of pebbles, cobbles, and or boulders. The composition, because there's so much here, I just went with the word variable, and the comments, they're rounded fragments. How will we fill this in for breccia? Find breccia, go over to the grain size. We see it's the same as conglomerate. We're going to go with it's mixed again. Again, we go from breccia, we go over to the composition. It's made out of all these different things. So you could either list them all, or again, we'll go with variable, made up of a variety of minerals. Yeah, shoot, got ahead of myself. Thank you. Oh, it's okay though. So again, variable meaning it's made out of a bunch of different things. So mixed, and then oh, I see. I guess I got way ahead of myself. So when I want an actual grain size, so this one's grain size name, this one's grain size centimeters. Everybody else has an actual number. So sandstone, let's do sandstone. Sandstone, it's the name of the sediment it's made out of is sand. And then it's got the size of the sediments underneath it. So 0.006 to 0.2 centimeters. And the comments for sandstone are just find a course. Sorry about that. Got in a hurry. And I guess we skipped for breccia. The comments were angular fragments. I think I'm gonna leave. Oh wait, there's one more thing I want to show you. Could you guys all flip your reference tables back to page 6? All right, so teachable moment here, because I think I asked you about this later on. So flip your reference table back to page 6. We're gonna look at the one and only rock chart chart we have not looked at yet on page 6. This reference table, we're not going to use it to its full capacity today. This is really for chapter 5, but there is some helpful information on this reference table. So the title of it is Relationship of Particle Size to Water Velocity. Really, this is a chart for how fast does the water have to be moving to pick up rocks and move them around. That's weathering and erosion. We'll do that chapter 5. But what this does tell us is the exact size of all of the different sediments. So again, some of them say, right here, clay is less than 0.0004 centimeters, silt 0.0004 to 0.006, sand 0.006 to 0.2. Those exact numbers, like for example here, here's the word sand. Notice how the dotted line above sand and the dotted line below sand, they're labeled 0.006, 0.2. So those are the same numbers you found right there. This one just tells us how big pebbles, cobbles, and boulders are. So before this, how big would you have thought a boulder had to be? Where are your hands? How big is a boulder? Humongous, right? A boulder is big. Here it actually tells you it just has to be 25.6 centimeters. Let me get you a ruler and show you how big that is. 25.6, 20, or is it 26.5? No, I forgot. 25.6. That's that big. That is a boulder. It's about the size of my head. So a boulder is, oh, that's a boulder. Is that what you would have called a boulder before? No. So boulders are actually a lot smaller than you thought. How big would you have thought a pebble would have been? Really small? And it is. It can be. It can go from 0.2 centimeters. So that's there. Up to, so 0.2 centimeters is right about there. Up to 6.4. So that's, you guys are about right. 6.4. So about that big. So that's a pebble. A lot of these rocks we were working with in lab, that's a pebble. Sand, pretty small. Silt, almost impossible to see. Clay, when you guys think of clay, what do you think of? You think of chunks of clay, right? Like when you're about to make like a pot in ceramics, you have a handful of clay. When I'm talking about clay, I'm actually talking about one individual speck of clay. Have you guys ever been in a ceramics room?
No.
Okay, those of you who have, do you remember the fine dust that's literally everywhere in that room? Yeah. Yes, that anything down on the tables, it's got a layer of dust on it. Yeah, those individual pieces of dust are the clay I'm talking about. If you guys have not experienced that, but you still pictured like a handful of clay, picture when your clay dries on your hand and you get like fine dust that you can like just brush off. That's what I'm talking about for clay. So not a hunk of it, but one teeny tiny, almost microscopic version of it. You think you guys can handle finishing page, what is that, 26? Yeah. That's your homework? Let me know if you need any help. So apparently we'll go over last night's homework and tonight's homework tomorrow. So those of you who didn't do it, you have a chance to do it for a late grade.